All right, good evening, everyone, and thank you so much for joining us for the Tornado Scientist Storm Chasing with Dr. Robin Tanamachi. This is a live virtual citizen science event hosted by the Carmel Clay Public Library. Dr. Robin Tanamachi is a research meteorologist specializing in the collection, analysis, and assimilation of mobile Doppler radar data collected in severe storms and in tornadoes. She currently works as an assistant professor at Purdue University in Northwest Indiana. Previously, she was a research scientist at the Cooperative Institute for Mesoscale Meteorological Studies in Norman, Oklahoma, which is closely linked with the National Severe Storms Laboratory. She's been an avid storm chaser since 2001 and has participated in numerous severe weather research campaigns, including Vortex 2 from 2009 to 2010 and Vortex Southeast since 2016. The library is pleased to virtually welcome Dr. Robin Tanamachi.
Thank you, Catherine, and hope everybody can hear and see my presentation okay. Can I get a thumbs up from folks if they can hear and see me all right? Okay, fantastic. So this presentation I've titled My Storm Science Journey because I wanted to tell you about kind of my journey from childhood to becoming an assistant professor of meteorology here at Purdue University, and just kind of bridge the gap between, you know, where did I come from and how did I get here. So to start off with, I just wanted to introduce you to you know, the book about me, which is what actually inspired my visit. And this is a book called The Tornado Scientist. It's a book targeting 8 to 11-year-old kids. I am not the author of the book. The author is a wonderful woman named Mary Kay Carson, who's based out of Ohio, and her husband, Tom Ullman, is her photographer. So got an author and a photographer teaming up to produce this wonderful Scientists in the Field series of books published by Harcourt Mifflin. Or Houghton Mifflin Harcourt, I'm sorry. And they contacted me back in 2018 regarding wanting to do a book about a tornado scientist, and they had seen some work I had done on a blog and on the Weather Channel during previous field programs and were interested in interviewing me for the book. And they also very kindly sent me some samples of previous books that they'd done. There was one called Emmy the Rhino Scientist. There was one about the Pluto New Horizons mission. And I read through them and was very impressed. I'm the mother of 2 small children, and you know, I'm always looking for great material for them to read in school. So was impressed by some of the previous books that she had done. And so I agreed to let her come storm chasing with me for one season, and she and her husband joined me for a couple of days, and we managed to catch them a tornado and take them. They got to experience life on the road and eating all the bad food and staying at flea bag motels and all the not so glorious things that don't get shown in the movies. And as a result, then this book was released in early 2020, right at the onset of COVID. And so, but I was really pleased with how it turned out. But that's the reason why nobody's wearing any masks in this book. It was a pre-COVID production. So that's just a little introduction to me. I wanted to, though, ask you all a question, and this is going to require you to maybe hop on a browser or on your phone and enter. There's a code at the top of the screen. So it's www.menti.com, MENTI, and the code number is 2291. 1320. And this is a word cloud. So as you start to enter your submissions, you will see your answers will pop up on the screen here. So I want to know, what is your favorite kind of weather? And this can be good, this can be hazardous, this can be something exciting, something not so exciting, like, you know, clear skies, sunny days, foggy. We have our first entry. So we have somebody here who likes fog. Fog isn't really my cup of tea, but I know some people who certainly do enjoy studying that and all of its vagaries. All right, we're seeing sunny, rainy, storming. A few storm fans in the house here. Let me put this link in the chat here too, if folks are having trouble with the screen. Supercells, somebody's in my ballpark here. Thunderstorms. And the more people enter a particular word, the bigger it gets. All right, we're starting to see severe weather, overcast, tornadoes, thunder and lightning, donder and blitzen. Very good. So yeah, it seems like we have a lot of sunshine fans in the house, so maybe not so many fans of the kind of weather that I study. I certainly enjoy sunny weather. I enjoy going on vacations to Florida. I enjoy hanging out on the beach and being in the sun with my kids and being able to play outside. But the place where I make my bread and butter really is with severe weather. So, all righty. Let's see, we got, and you can enter more than one thing too, by the way. It will allow you to enter, I think, up to 3 times. So if you've got more than one kind of weather that you like, go ahead and put that in. This is just kind of for me to get an overview of where you all fall on the weather spectrum. There's people who are kind of weather-wise, and as Ben Franklin said, some are weather-wise, most are otherwise. But thunder, snow, excellent. I see a reference to a date there, 4/27/2011, and that's a date of a significant tornado outbreak in the Southeast United States. Very good. All right, so I'm seeing a very good variety of weather ranging from winter to spring to summer to fall weather. Somebody mentioned specifically. I'm seeing a range from, a lot of people like sunny weather, but some people also like severe weather. Some people like blizzards, some people like thunderstorms. So it takes all, and weather has the same sort of properties that people's personalities do. Some people are sunny, some people are severe, some people are kind of foggy. So I think that, the kind of weather that you really enjoy does say quite a bit about your personality. So it's good to see a variety of personalities and weather types represented here. All right, thank you guys. I'm going to flip back over to PowerPoint now. So a little bit more about my background and my superhero origin story, if you will. So I was born and raised in the Twin Cities area of Minnesota, although this picture wasn't taken in Minnesota. This was many years later. As a child, I always knew I was really interested in meteorology, wanted to be a meteorologist since I was about 5 years old, the age my youngest child is now, and ended up going to the University of Wisconsin-Madison to get my Bachelor of Science degree in Atmospheric and Oceanic Science, because that was the closest major meteorology program in a college to where I was born and raised. University of Minnesota didn't have it, and Wisconsin was the nearest school that had reciprocity that I was able to attend and get that degree. Subsequently, I took a year off actually and did an internship at a place called the Space Science and Engineering Center at UW-Madison. And at the conclusion of that year, was advised I should really go on to graduate school. I was doing really good work, and they thought that I could really hone my research skills going to graduate school. They knew I liked severe weather, so they suggested that I apply to graduate school at the University of Oklahoma, where I was fortunate to land a research assistantship under Professor Howie Bluestein, who's kind of a big deal in severe storms and tornado meteorology. So I ended up getting my master's and my PhD, both from the University of Oklahoma, both in meteorology, and both doing theses and dissertations on tornadoes specifically. And as part of that, I got to work with a bunch of different mobile radars. So there's me pictured with one of the smaller ones that I use, mounted on a Ford F-350 chassis. Got to drive that around the plains and use it to scan severe storms. But that was the start of a very long journey through many different kinds of field work using different mobile radars of different sizes and other kinds of equipment. So probes that we could drop in the path of storms, hydrologic measurements. I also did a lot of computer programming, so numerical weather prediction, and what's called data assimilation. So that was the marriage between radar meteorology, so observations of storms in 4 dimensions, and actually assimilating those data into a numerical weather prediction model in order to recreate storms inside of a computer and see how they work. Following getting my PhD in 2011, I did 2 postdocs. One was at a place called the Center for Analysis and Prediction of Storms for a year, and then at the National Severe Storms Laboratory, which is a place I had always wanted to work. And that was for 2 years under the wonderful Dr. Pam Heinzelman, who is one of my best friends and greatest mentors. So it sounds like I'm moving around a lot, but really all these places, the University of Oklahoma School of Meteorology, Center for Analysis and Prediction of Storms, National Severe Storms Lab, they were all housed in this building here pictured behind me, which is the National Weather Center located in Norman, Oklahoma. And that is where all the weather geeks go to hang out and watch the storms come. It's a real powerhouse of radar development, severe weather observations, numerical weather prediction, development, computer programming, basically anything that we have. All of our modern warning infrastructure was developed in and around Norman. And so we got a building as a result of the May 3rd, 1999 tornado. We got a big building, big shiny building to train students and get them experiential learning, working in the field with all these different instruments. Following that, I got an offer to come here to Purdue to work in the Earth, Atmospheric and Planetary Sciences Department, EAPS, here at Purdue, with my husband, Professor Dan Dawson, who's also a professor here at Purdue. So we work side by side now. We're bringing a little bit of that Norman weather community and weather spirit here to Purdue, and the students are just absolutely loving it. We take them out storm chasing on the plains every year, and I'll talk a little bit more later about what that involves. But just getting back to, way back at the beginning. So I'm 6 years old and I'm home for the summer, one summer in the 1980s. And my dad comes running downstairs and says, "Robin, you have got to come upstairs and see what's on TV right now." And so I did. I came running upstairs to the only TV set we had in the house. And there was this tornado on TV, and it was being captured live from a television news helicopter. And I show this video not only because it rivals some of the drone footage that we get even today, but just because, I was absolutely captivated as a little kid by just the twisting and the helical structure that this tornado had. And I was just enchanted. And basically that tornado grabbed me and never really let go. So in the months and days following the live airing of this video, of course, the TV channel, it was a NBC affiliate, Channel 11, based out of the Twin Cities, and they played this video every opportunity that they got, just ad nauseum, over and over and over again. And during one of those subsequent replays, they actually brought in via satellite from Norman, Oklahoma, a gentleman named Don Burgess, who was then working at the National Severe Storms Laboratory, and he talked about how this sort of helical structure that this vortex had heretofore only been seen in physical laboratory models, and those laboratory models were actually built here at Purdue, coincidentally. And so they'd only ever seen that kind of a vortex structure in a laboratory model. And he was explaining the significance of this being captured on video in such great detail and done safely. And that was the first time I had ever heard that there were actually scientists whose job was to study tornadoes. And I decided that was what I wanted to do. So I refer to this tornado, the Fridley, Minnesota tornado of July 18th, 1986, as being my gateway tornado. So just to put this in context, so I grew up in Minnesota up here, which is not exactly a hotbed of tornado activity. We still get, we could get quite a few per year, but not nearly as many as they do in the more traditional tornado alley states. And, we're here in Indiana, which again is not, really considered to be in the heart of Tornado Alley. But, we still get a not insignificant number. It's enough that we have to teach kids in schools how to take shelter, how to take their, tornado precautions, where to go in case a tornado comes, when mom and dad aren't home, that kind of stuff. So these are just the raw numbers, and you'll notice Texas is up in the red, but that's mostly by virtue of the fact that Texas is just a big state. And as a result of its large land area, it gets a lot more tornadoes per year than just about any of the other lower 48 United States. But if we normalize by area, so if we divide through by the number of square miles in each state, then we get a more coherent picture that's actually centered on the regions around Oklahoma and Kansas, where we get, on the order of about 11 per 10,000 square miles per state. So this is a little bit more of an apples to apples comparison between the states. And you'll notice that, again, Indiana, not one of the top tier states, but we're definitely, kind of in the second tier. And there actually is some research that was done by Dr. Ernie Agee here at Purdue, suggesting that sort of the center of gravity of where we consider Tornado Alley to be has actually shifted a little bit to the east from Oklahoma into, maybe Arkansas. We're seeing a lot more of these Southeast US tornado outbreaks that are having a severe impact. And that's actually been the impetus for some research that we did as a part of a project called Vortex Southeast, where we were investigating factors contributing to some of the high mortality rates in the Southeast United States, and whether is there something physically different about the storms in the Southeast United States that lead to these disproportionately high fatality rates? Or is it just that, people down there don't have the infrastructure, aren't getting the warnings, or they don't know how to act on those warnings appropriately? And it turns out it's a mixture of both. The storms down there produce tornadoes that tend to have very low wall clouds that kind of scrape the tops of the trees. You may not see or hear the tornado coming as well. And people down there also experience a lot more poverty. They're in a lot more manufactured housing, things that increase your exposure to severe weather risk and hazard. And so we think that those things in combination are contributing to the high mortality rates that we saw in the 2011 outbreak and also in subsequent years. So just to get back down to basics. So what makes a thunderstorm? And I think of it as a recipe. You have these 4 primary ingredients that we have to have in juxtaposition with one another. So they all have to be overlapping, one stacked on top of the other. And those 4 ingredients are moisture, instability, meaning the air has to cool off with height at a certain rate or faster. We have to have a source of lift, so something to get the storm to form in the first place. And you also have to have wind shear. And wind shear refers to either the change in the speed or direction or both of the wind as a function of height. So as you go up in the atmosphere, the wind vector comes from a different direction or blows faster with height. So all 4 of those things have to be present in order to get severe thunderstorms to form. And if any one of those ingredients is absent or is weak, then that may change the character of the storms. You may get no storm at all if there's no source of lift, for example. You can have all the instability in the world, but if you don't have something to actually initiate the storm in the first place, you may not get a storm to begin with. Or, if any of these ingredients are present but in very low quantities, then you may get storms of a different nature. You may get a squall line instead of supercells. You may get single cell thunderstorms instead of supercells, that kind of thing. So all 4 of those things have to be located together. So this is what we refer to literally as the ingredients-based method for severe storms forecasting. That was a phrase coined by a couple of scientists named Bob Johns and Chuck Doswell back in the early 1990s. And it's the basis of our severe weather forecasting system that the Weather Service uses even today. So storms can take on myriad structures and forms. And we'll start with the basic Lego brick, if you will. The basic building block of severe storms is the single cell storm. And that consists of a single cell thunderstorm, one updraft, one downdraft, and it has a very predictable life cycle. These tend to form in these weak shear conditions where you do have the instability present, but maybe not so much the shear. And basically it starts off, and this conceptual model was developed back in the 1950s during a project called the Thunderstorm Project that took place in Ohio and also in and around Oklahoma, where they just basically studied the heck out of every thunderstorm that formed over those areas and were able to then build up this sort of generalized model of the life cycle of a single cell thunderstorm. And that consists of 3 stages. Initially, you just have a towering cumulus stage where you just have a single updraft and it may be accompanied by clouds. Then it reaches a mature stage where the storm actually hits what's called the tropopause, which is a very stable layer of air up around 10 kilometers above the surface. And the cloud actually starts to spread out sideways. It starts to precipitate and produces a cool downdraft, which spreads down and around on the ground. And that can actually undercut the updraft. So it cuts storm off from its source of fuel, this moist, unstable air near the surface that it needs to loft and make condensation. When that condensation forms, it releases heat that turns the storm into more of a self-sustaining organism where the parcels that start to rise keep rising, and it can keep going then for up to 30 to 60 minutes. Now, at some point, the downdraft overwhelms the updraft, completely cuts off the updraft from its source of warm, moist, buoyant air, and you're left with just a pure downdraft at the end. So what goes up must come down, and eventually the storm dies. And you're left with what's called an orphan anvil up here near the top. Maybe a little bit of residual precipitation, but eventually that'll rain out, the sky will clear out, and things will go back to quiet. So this is our basic building block. Now, mute that, but this is a time-lapse video from Weather Service out in Riverton, Wyoming, of a single cell thunderstorm forming over the high plains. So we've got initially we just have our towering cumulus cloud, a little bit of glaciation at the top. You can see it's starting to precipitate. You can see a rain shaft starting to form underneath it. And you can see the updraft is starting to hit the tropopause, starting to sort of pancake out as it hits the tropopause, that stable layer of air up around 10 kilometers and spread out. But the updraft is still convectively active. And if you trace any of these little cloud tags as they're climbing up the side of the updraft, they're still rising. So you still got an updraft, but then you also, on the far side of the storm, with respect to the camera's view, you have a downdraft associated with this precipitation that's falling. And eventually that downdraft will overwhelm the updraft and start to cut it off, and the storm will begin to die. So you may hear meteorologists refer to single cell storms as what are called pulse storms or garden variety storms, or you may also hear the term air mass thunderstorms, although that's not favored because that makes it sound like the storm is forming in the middle of a uniform air mass, and usually it's not. It's usually forming near some kind of a boundary. It may be just, an outflow boundary from a nearby storm. So our life cycle, again, we're looking at 30 to 60 minutes total. And primary hazards are going to be just, very brief local heavy rain and gusty winds, and maybe if the updraft is strong enough, maybe some pea-sized hail out of it. But generally the hazards are not that great with these guys. This is what they look like on radar. Basically, you just have radar zits. So individual storm cells that are kind of moving along very slowly, or they may just sit still sometimes. They may just sit still and produce these circular outflow boundaries that flow out in different directions and may instigate new storm formation. This is an example from last summer here over southern Indiana. If we crank up the shear a little bit, so that fourth ingredient, we crank up and add a little bit more shear into our batter, we can end up with something called a multicell storm. And that is where you've basically got, what would be a single cell storm forming over here on the left, but it's being pushed downstream a little bit by stronger winds up aloft. And so by the time the storm gets to its mature stage, it's now displaced enough from its location of origin that new cells can start to form behind it. So what you end up with is a train of cells, each at a different stage in its life cycle. So as it matures, it starts to precipitate, produce these downdrafts, and then you've got the dying storms over here on the right. So the oldest cells are here on the right side of the diagram, and the youngest ones are here on the left. So you can end up with these training cells that can actually persist over a single area for a very long time. So as a result of that, you can end up with hazards for flooding rains. So downpours that last quite a while. You can have storms that kind of train over the same area for a long time. So say near Charleston here on this little map, you've got a series of cells that are passing over Charleston over and over again, and may drop heavy rain in a very narrow band over a long period. They can also be responsible for downbursts and gusty winds and maybe some small hail if there's enough instability in the atmosphere. But these are slightly more complicated than our single cell. So you think about our single cell, now we've got a series of them kind of training and chaining together. Crank up the shear even more, and you can get something called a squall line, also known as a quasi-linear convective system, also known as a mesoscale convective system, also known as a derecho if it gets big and strong and long-lived enough. And these are the kind of storms that, basically they're very hard to photograph because you'll see this almost this mothership cloud coming at you, and it stretches from one horizon to the other. Big shelf cloud kind of rolling out at you, very dark and foreboding behind it, maybe some hail. And these can span thousands of miles in whatever direction perpendicular to where they're traveling. They basically are a organized linear type of storm that basically produces its own cold pool and then surfs that cold pool. It rides on that cold pool as it scoots along the landscape. And if the conditions are right, if there's a long enough fetch of instability, say in this image on the top here, which by the way, this is not all taken at once. This is a composite of several different times in the lifetime of this derecho as it's marching in 3-hour intervals all the way from eastern Texas, northwest Arkansas, through the southeast tier of states and off the coast to the Atlantic and off of Florida, basically over the course of 24 hours. So these storms can be exceptionally long-lived. They can produce extreme gusty winds because, again, they're riding along this gust front, which is being continually reinforced from behind by a descending rear inflow jet, and it just surfs all the way along until it either runs out of instability or or some other process in the atmosphere can maybe disrupt it. These are generally not tornado producers, although they occasionally do. And in fact, there is a field program going on right now called Perils, which is looking at the tornado genesis in systems like this. And my husband, Professor Dawson here at Purdue, is participating in that field program right now. So he's going down to the southeast tier of states every couple of weeks to sample these squall lines as they go through. They've gotten 4 really good squall lines, each of which produced a tornado so far. So they can and occasionally do produce tornadoes, but generally the main hazards associated with these guys are going to be extreme gusty winds. So think like the Sugar Land, Indiana Stage Fair collapse from a few years ago. That was instigated by one of these squall lines moving in. Climatology for derechos, they tend again to cluster in the very same places that your traditional tornado alley states stretching from Texas all the way up to southern Minnesota might fall. But Indiana is no stranger to derechos, no stranger to squall lines. We get usually several squall lines a year and maybe one derecho every year. We're not in the top tier of states. That honor is reserved for southwest Missouri, northwest Arkansas, northeast Oklahoma, but we certainly are in that second tier of maybe getting a derecho every year to 2 years. Now we crank up the shear a little bit more and we add a little bit more directional shear into the mix. So we've got a combination now of really high instability, high amounts of wind shear, lots of ample moisture available from the Gulf of Mexico, and then a source of lift, which is usually provided by something called the dry line, which is like a air mass boundary that separates moist and dry air that sloshes back and forth across Oklahoma, Texas, Kansas, and parts of Nebraska almost daily in the springtime. So that provides an ample source of lift. And so this is why, because we get the juxtaposition of those 4 ingredients, that's why tornadic thunderstorms, supercells, form over that region of the country the most often. So we end up with supercells being the most organized and hazardous type of storm. They have a very specific shape on radar. They have this sort of eagle's head shape with a hook echo region down at the end. This is what we call the business end of the storm, where the tornado is most likely to form. That curl is indicative of the rotating updraft within that thunderstorm. So raindrops are actually being entrained into that rotating updraft, being turned around and lofted as they go around the mesocyclone. And then underneath, and the mesocyclone is the technical name for that rotating updraft in the interior of the thunderstorm. And at the base of that mesocyclone, that is where we generally find the tornado. So here's some of the corresponding features that you might see if you were out in the field looking at a storm like this from, say, the south or southwest. We've got a flanking line. So these are our single cells that are trying to form, and they're actually being ingested into this much larger rotating complex of updraft that constitutes the meat or the bulk of the supercell. These are what are called cumulonimbus clouds. They have this very crisp cauliflower-like appearance, and especially this part here at the top, the overshooting top, that's indicating where the strongest updraft is actually punching up through the tropopause, punching up through that stable layer at the top, and it's briefly able to shoot up and bubble up over the top of it just for a little bit before it dies back down. The updraft is so powerful that when it hits that atmospheric lid at the top of the tropopause, it has no place to go except sideways. And so you get this very broad anvil cloud, which tends to spread downstream. A lot of the heaviest precip and hail are going to fall just a little bit downstream of that updraft, and then where the updraft meets the downdraft region, and that downdraft region is curling back on the backside of the storm from respect to our view toward us, and down and behind where we get an interface between the updraft and the downdraft. We get something called a wall cloud, which is this blocky lowering in the cloud base that marks the location where the updraft and the downdraft are meeting and trying to duke it out. And that is the likeliest location for us to find the tornado. It doesn't always form in this location 100% of the time, but if I'm going storm chasing with a radar and gas is $5 a gallon, you bet I'm gonna target this area of the storm, because that's where it tends to form the most often. So the analogy I like to draw is, let's say you were going to Yellowstone National Park and you wanted to see Old Faithful. Well, you'd get a map of Yellowstone National Park and you look up where Old Faithful is, and you'd plan when to go to see it when it erupts. So I like to think of a supercell thunderstorm as kind of like a national park that's only going to be there for about 6 hours, and it's going to be moving 30 miles an hour the whole time. So I have to be able to predict where Yellowstone National Park is going to pop up. I'm going to have to be able to be in position relative to Yellowstone National Park in order to see Old Faithful, the tornado, when it's erupting or dropping out of the wall cloud, and then, follow it along until it dies. So just imagine if Yellowstone National Park was only going to be there for 6 hours and you had to follow it, and it was moving the entire time. That's kind of the challenge that arises with storm chasing. We have to do good forecasting many hours in advance, even days in advance. We have to be in the right location relative to the storm in order to see and document the tornado, either by video or using a mobile DualPoll radar, which I'll talk a little bit more about here in a little bit. And then we have to be able to target and get the kind of data that we want. So, you may go all the way to see Old Faithful and it may be foggy that day. You might not actually be able to see it. The tornado may be rain wrapped too. You may not be able to see it with your eyeballs. You just have to be there at the right time in order to catch a good view of it. But supercells are by and large responsible for almost all strong to violent tornadoes, almost all giant hail, and destructive downburst winds. Basically all types of hazardous weather are possible with the supercell. So these guys are ones to watch out for. And when you see a place like the Storm Prediction Center promote a high risk for a particular day, that's usually because they see the ingredients for supercells coming together and they perceive a high risk for all of those threats. So just to show you what a supercell looks like, this is a time-lapse video. It's not mine. It's from some of my friends at a group called the Base Hunters Chasing Group. And this is shot from the roof of their car, roof cam of their car. And you can really see that rotating updraft. So the entire storm is rotating, not just the bottom part of it. I don't think there's actually a tornado in this video, but I just wanted to show you this to just show the pure majesty of supercell thunderstorms and just how spectacular they can be, even when there's no tornado present. They're really amazing to watch. They evolve. They all have personalities. And, we still have to play it safe around them. There's still hazards like lightning, or maybe you'll be watching one tornado and the supercell will drop a second tornado on top of you. You really have to be careful. So you'll notice these people are kind of driving and moving out of its way periodically as it comes toward them. But you can really see the updraft and the barber pole striations in the updraft of this storm. So it's definitely a rotating updraft. Let that go ahead and play out. And these can persist for many, many hours. So, and I'd consider this to be a good chase day, even if there was no tornado, because you get to see a really spectacular storm at the end of the day. So just to summarize, I've gone over the 4 ingredients that we need for severe thunderstorms. We need the moisture. That's our source of buoyancy. So parcels of air can rise. We need instability, so that an environment that's conducive to rising air. We need wind shear in order to get the storm to rotate in the way that we want in order to get tornadoes. And then we also need a source of lift, something to instigate that updraft rising in the first place. And by the way, I have to give a caveat here. Whenever I say conditions are good for storms, or we want this, I'm talking about, people like me who are actually trying to target these storms for research. We never want to see property destruction. We never want to see people get injured. But we want to do our research. We want to, meet the objectives of our research grants too. So we hope for storms, but we also hope that those storms stay out over open country where they don't hurt anybody and don't do any property damage or wreck anyone's life. All right, and then the other four in this 4x4 is the four main types of storms. So I built up from the simplest kind, the single cell storm, to the multicell, which is a complex of single cells at different stages in their life, to squall lines or QLCSs, which are these long linear storms that can persist for many hours, up to and including, derecho strength, which tends to be these very widespread wind damage events like we had in Iowa last year. And then there's the supercell, which tends to be a lot more compact, a lot more isolated, but is the source of virtually all violent to severe tornadoes and all gigantic hail events that we see here in the United States. And each one has a different set of associated hazards. That doesn't exclude a particular kind of storm from having a particular kind of hazard, but so always be prepared for all kinds of hazards with storms, but just know that some hazards are more likely than others. Like tornadoes are definitely going to be more likely with supercells than they are with any of the other three categories of storms, for example. And also they can change as they move in from one environment to another. Maybe the wind shear increases as time goes on. Maybe they gain or lose access to moisture. The character of the storm can actually change as time goes on. So you may have a storm that starts off as a multicell, eventually hits a nice patch of wind shear and turns into a supercell. You may have a supercell actually get eaten by a squall line. We see that kind of thing happen all the time. So you can have mixed modes. You're not limited to just having one mode of storm. Okay. So that's storm basics in a nutshell. If you want to know what kind of storms are likely on a particular day, and as we get into storm season, would strongly recommend that you bookmark the Storm Prediction Center website. This is a NOAA specialized prediction center that is located in, surprise, surprise, Norman, Oklahoma. They were just downstairs from me when I was doing my dissertation and my postdoc. And this body, the Storm Prediction Center, is responsible for issuing all of the tornado and severe thunderstorm watch boxes for the lower 48 United States. So anytime we are under one of those watch boxes, like we were just west of here yesterday, that watch box came from a room in Norman, Oklahoma that is filled with degreed meteorologists who eat and breathe this stuff, and they are on duty 365 days a year, 24 hours a day. Issuing watch boxes and what are called mesoscale discussions, so more detailed discussions of particular storms or particular storm environments and how they're evolving. And they communicate with these 120 plus local National Weather Service offices. And your local Weather Service office is the one in Indianapolis that covers you. And so they're going to be in communication with the Storm Prediction Center in Norman all the time, coordinating on these watch boxes. And then the warnings come from our local National Weather Service offices. So just to get into some nomenclature about the difference between a watch and a warning. So watch is sort of a lower category of alert. It means hazardous weather is possible at some point in the future. The ingredients are there or are forecast to come together in your area in the future. And so that's your notification to put your action plan into effect, to have a place to go, have your tornado shelter swept out and get all the black widow spiders out of it. To get your disaster kit together, to gather all your important papers and things and have those in that place. So that if you have to do later on, if a warning does come out, which means hazardous weather is occurring, imminent or likely, that you can very quickly take evacuative and protective action to protect your life and property. So the warning, again, that's a higher level of alert, and that means that the hazardous weather is occurring, imminent or likely. There's an imminent threat to life or property, and people need to take action. So that is your call to action, and there will be a call to action statement in the warnings that come out of the National Weather Service. So all watches and warnings are issued by the National Weather Service in the United States. You may occasionally see TV stations issue their own warnings, but the official warnings that come from the Weather Service are the ones that are, issued by your local Weather Service forecast office by degreed meteorologists who know what they're talking about. So, so always give credence to those when they do come out. Just to explain the difference a little bit further, on the left here, we have what's a cupcake watch, where you have all the ingredients kind of coming together in the same location, but the cupcake hasn't formed yet. And on the right here, we have a cupcake warning where the cupcake has actually been formed and is ready to eat. And I know all of you are probably going to run out to Gigi's now after this. All right. So my research on severe weather involves radars. And I love radars because basically they are one of the only instruments that we have in our arsenal that allows us to image entire storms in 4 dimensions quickly and safely, because we can do it from a distance. So just to give you a basic low-level overview of how radar works, radar will transmit microwave pulses of energy out into the atmosphere in a particular direction, and then listen for the echo from that microwave. So it's not something that's audible to your ears. It's microwave frequencies, which are around 1 centimeter to 10 centimeters wavelength. And those will interact with water drops. And this animation is a little bit misleading because it kind of makes it look like the water drops are just bouncing the waves back to the radar. What's actually happening, though, is that the raindrops are actually absorbing a little bit of the energy from the microwave photons, and that actually heats them up a little bit. It actually excites the water molecules, and then those molecules will re-radiate the microwave photons in all different directions. A little tiny bit of that comes back to the radar. All of this happens thousands of times every second. It's much, much faster than any of us can perceive. And so we're pulsing the atmosphere with this large amount of energy, getting back a small amount of energy, and we're able then to map out the location and intensity of precipitation in space. Now, other stuff in the atmosphere besides raindrops can actually echo back to the radar, and that includes things like bugs. If you think about it, bugs are mostly water and they're approximately spherical. Same goes for birds. Same goes for cloud droplets that are not actively precipitating out of the storm. Also things like aircraft, which are large and metallic and highly reflective at microwave wavelengths. Chaff, which is a substance that's sometimes ejected from fighter jets in order to confuse enemy radars, so that heat-seeking missiles and other things will actually follow the chaff rather than following the target aircraft. Also, regions of strong ionization can lead to the alignment of ice crystals and polarization of the returned wave sometimes. You get really bizarre interactions with the upper levels of the atmosphere, but I'm more interested in the lowest 10 kilometers, the troposphere, which is where all the weather action happens. So collectively, we refer to these things in the atmosphere as scatterers. So when I use the term hydrometeor, that's a generic catch-all $6 word that can include things like raindrops, hail, snow, cloud droplets. Anything that's made of water that's out there in the atmosphere is a hydrometeor. Okay. Well, I study tornadoes, and tornadoes are, despite their prominence in the United States, we get more than 1,000 tornadoes a year, but they're still a relatively rare phenomenon. So if tornadoes don't pass by fixed site radars that often, researchers, we put these radars on trucks, we make them portable. We take them out into the field and try to bring the radar to the storm rather than waiting for the storm to come to us. And so that's what I got to do as a graduate student. So here's a picture that I took when I was on a field program called Vortex 2 back in 2009. And there's my engineer, Christoph, operating this radar truck. The dish is actually behind this black shield here, so you can't see it. And you can see this kind of grayish smudge in the background. That is a developing tornado that lasted about 8 minutes. And the reason Christoph is pumping his fist in the air and he's so happy is because like 3 days before I took this picture, we thought this radar was dead. We thought that the transmitter was broken in a way that would not be repairable by the end of the field program. But Christoph, my engineer, pulled some engineering witchcraft and was able to revive the radar, do some CPR on it and get it running again. And we were able to go back out in the field and we got this tornado on that day. And I actually got a paper out about this. So these are the data that we collected. So just to orient you, the radar is located at the point of this sector here, and we're scanning back and forth horizontally. So we're taking horizontal cross sections through the storm as it's producing this tornado. And I'll wait till this kind of rewinds itself. But you can see we're looking at the hook echo region of the storm. This is a very short range radar. It's one of the most nearsighted ones in the fleet of mobile radars that we take out to study severe storms. So here's our hook echo, the business end of the storm, and it's wrapping up. And you see this little eye open up in the middle of the reflectivity. image. So we've got rain curtains wrapping around the tornado, but in the middle, there is this rapidly rotating column of air that's actually centrifuging raindrops out of it. And so you get this rain-free column right in the middle. That little eye that opens up in the middle of the tornado is almost a sure sign that there are tornado strength winds going on. The right panel is what's called Doppler velocity. So that is motion toward or away from the radar. So the warm colors, the yellows and the oranges, are flow away from the radar. So air moving away from the radar. And on the cool colors, the greens and the blues, are air moving toward the radar. So if you kind of think about, mentally superimposing some wind vectors over that, what that's telling us is that we've got some air moving toward the radar on the left side and air moving away from the radar on the right side. So you've got rotation in here. You've got a rotation circulation in and around this developing eye. So there's definitely a tornado going on here. This whole sequence is about 8 minutes worth of data from beginning to end. And we were able to see a funnel cloud for most of that period. So not to be outdone, though, we've gone and outfitted a lot of our mobile and now our stationary radars with what's called dual pol technology, dual polarization radar, which is where we can control the polarization of the electromagnetic field that's associated with each pulse of microwave energy that's going out. And it can be oriented either in the horizontal polarization, so that's this sort of flat wave going out here, or in the vertical polarization. So the electric field is polarized vertically. And those are going out into the atmosphere and interacting with the hydrometeors out there. Most hydrometeors are going to align in the atmosphere with their principal axes, their longest and shortest axes, aligned with either the horizontal or vertical dimension relative to local gravity and the local Earth surface. So we can exploit that to learn things about the shape of the raindrops. Here you'll notice the raindrop is not teardrop shaped, it's actually hamburger bun shaped. And it turns out that the more water mass is associated with a raindrop, the bigger and flatter it gets. So the more energy we get back in the horizontal channel than in the vertical channel, because the wave is having to travel through more stuff and scatter back through more stuff. So we can actually estimate the size of the raindrops based on how much energy we get back in the horizontal versus the vertical channel. Hail tends to come back with about equal amounts in the horizontal and vertical channel. Snow is kind of a mixed bag because it depends on the mode of snow. Sometimes we get these big fluffy dendrite kind of snowflakes, and sometimes we get ice crystals that are vertically oriented. So we can tell something about what's called the habit of the ice crystals based on what readings we get back in the horizontal and vertical channels. So I got to work with, and as of 2013, all of the National Weather Service's radars now are dual pol. They still only update every 5 minutes, though. And that is something that we're trying to overcome now with more of these rapid scan radars, but marrying the rapid scan technology, so having faster than 5-minute updates with the dual polarization technology, is a huge engineering challenge. I don't totally grok all of that, but a lot of my engineer friends are actively working on that problem. So I got to work with one of the first mobile dual pol radars in the field. This one is called UMass X-Pol, and UMass because we rented it from the University of Massachusetts, who built it. And we took this out into the field for several seasons when I was a graduate student. And I include this picture because not only does it show UMass X-Pol with its 2 wave guides and two transmitters in their boxes, but also the fact that we were in the field on May 4th of 2007, and I was driving the truck, and all of a sudden the truck started to kind of shimmy, and I pulled over. It turned out we had lost the tread on the back tire, because this pedestal here weighs about 2 tons. It's really heavy, and we go through back tires like crazy. So as you can see, we're in this heavily populated area. Storms haven't started to form yet. We're getting a few bubbling cumulus clouds, but the cap hasn't broken. Storms haven't formed yet, but we're mounted on a Ford F-350 pickup truck, and we're in rural Kansas. Farmer rolls up, and stops to see if we need help. And it turns out he's also driving a Ford F-350 pickup truck, and his spare tire actually fit on our truck. So we were able to bum that spare tire off of him and limp to the nearest town, where we were then able to return his tire to him by our own and put it on. By then, though, we had lost several hours to that little mishap. And so we thought we were way out of position, and we're not going to get any good data that day. But what happened later in the day was that a storm formed over the town, and here's the grain elevator in that town of Protection, Kansas, where we changed our tire. A storm happened to blow up there, and we happened to see not 1, not 2, not 3 tornadoes, although you can see the second and the third are in this picture here, and that's the screenshot in very low light from a video that I took. Not one, not two, not three, not four, but 5, 6, 7, 8, 9, and 10 tornadoes. And number 5 turned out to be a biggie. It turned out to be the first EF5 following the introduction of the EF scale in 2007. So we had the Fujita scale for measuring tornadoes before this that went from F1 to F5. In 2007, they debuted a new enhanced Fujita scale, which corrected some of the flaws in the original Fujita scale. And so this was the first EF5 that was recorded following the introduction of that new scale. Unfortunately, it was rated EF5 because it destroyed 95% of this town of about 1,100 people called Greensburg, Kansas. There were only 11 fatalities in that town. And I say that, because it could have been a lot worse. But there was a very competent person at the scope in Dodge City, Kansas, watching the radar, saw this huge tornado forming and issued a tornado emergency for the city of Greensburg, which is actually one level higher than a warning. It's reserved for probably the top 1% of all tornado warnings. And that caused people to get into their basement shelters and take evacuatory action, so that even though this huge tornado, which was over almost 2 miles wide, passed directly over the center of town, decimated almost all of the buildings in town, there were comparatively few fatalities when you consider that there were 1,100 people living here at the time. So these data ended up becoming the nucleus of my dissertation, and I actually wrote my dissertation on the Greensburg tornado and looking at some of these dual pole data. So we have our traditional, like I was showing you before, reflectivity, so a measure of the intensity or concentrations of scatters. And you can see that not only does this storm have a hook echo, it's also wrapping back in on itself multiple times. So extremely powerful circulation in here. Our Doppler velocities, our outbounds are, upwards of 70 meters per second. Our inbounds are on, the low end of probably 20 to 30 meters per second. And that's because the storm is moving away from us. So we're adding a vector component of motion away from the radar. Over here, we have some of our dual pole variables. So we have something called ZDR. So that's the difference between the horizontal and vertically polarized reflectivity. And the bigger that number is, the bigger and fatter the drops are. So these reds correspond to big fat drops that are being entrained into the tornado circulation and actually centrifuged out. And then over here on the right is something called correlation coefficient, or CC. I have it annotated here as ρHV because that's what we use in the scientific literature. Rho is a correlation coefficient, Pearson correlation coefficient from statistics. So that's a correlation between the horizontal and vertically polarized signals. Where that number is close to 1, so where it's red and up around 0.9 to 1.0 is where we have meteorological scatterers, so our hydrometeors, our raindrops, and our hailstones. Where that number is low in the center of the tornado is where we have randomly oriented non-meteorological scatterers. So chaotic stuff, debris, leaves, twigs, parts of houses, dirt, cows. So all of those things have been entrained into the tornado and are actually being lofted to the height where we're actually scanning the tornado with our radar. So this was confirmation that we had a very large and destructive tornado going on. And I was able then to make some, very informative sort of forensic meteorology on this storm as it was approaching Greensburg. We ran out of radar power before we got to Greensburg, but we were able to get basically the developing stages and see how it grew. So just a diagram of what one of these supercell thunderstorms looks like, just as a seg into kind of the work that I do here at Purdue. Just checking on the time here. Oh my, I'm running low on time. But so, I mentioned, supercells have this big rotating mesocyclone in the middle of it. That's our powerful updraft that really makes the supercell what it is. And that feature we found out shows up in dual polarization radar data as a ZDR column. So a vertical extrusion of high ZDR values. So those big fat drops are actually being sucked up into the mesocyclone and being drawn up into the updraft. And that can be a pretty good indicator of how strong the updraft is, what the vertical winds are like. And there's also this extension horizontally down at low levels called a ZDR arc that extends far and away from and wraps around the hook. And there's some hypotheses that, the way that this ZDR arc changes, morphology, extent, aerial coverage with time may actually correlate with tornado genesis as well. So my current funding from the National Science Foundation is to investigate these two features, the ZDR arc and the ZDR column, to see how they change in the 5 minutes prior to tornado genesis. And to do this, I'm using a brand new radar, what's called a phased array radar. So instead of having a dish antenna that rotates in around and around, we have just a flat panel antenna, and this cover here is covering up about 2,500 transmitting elements. So each one of those is like a little tiny radar, and we can actually phase those guys in sequence, and we can actually form the beam electronically rather than mechanically. So instead of having to turn the antenna to scan the atmosphere, we can just phase the elements and actually scan a full 90 degree by 30 degree volume of the atmosphere electronically without moving the antenna at all. That means we can scan up to 6 times faster. So here I am out in the field with some students back in 2019, and we're getting ready to hit the road. So I'm training them on how to set this radar up. There's my graduate student, Milan Sharma, setting up the radar. We've got a cover that we have to take on and off every time we deploy the radar. When we stow the radar, it stows flat. So I'm just going to show you a little video about and this is about 4 minutes long video of us in the field using the radar. And just keep in mind as you watch this, that it's kind of a commercial for the Raytheon company. They got wind that we were using their radar to scan tornadoes, and they sent a film crew out with us one summer. So just keep that in mind here while I show you guys this video clip. The shear gets worse the further south you go. Based on that, I'm going to recommend we go west and just evaluate hour by hour as the day progresses. We start the day with a weather briefing, and that's usually led by the students. So we decide where we're going to travel to, if any. If we're not already in the target area, then we spend a couple of hours driving to that target area. In choosing a target area, we're looking for things like the availability of moisture, a source of lift, a source of wind shear. Those are all ingredients that we really need in order to get thunderstorms to form. So we're looking for a confluence of those ingredients. And if they're not where we are when we wake up, we need to travel, and that may be several hundred miles of driving. Left on Highway 69. Once we get there, then we start launching our weather balloons to sample the environment. And if we like what we see in the environment, we may stay put. If we don't like what we see, we may reposition a little bit, maybe another 50 or 200 miles. And then when storms actually start forming, that's when we break out Skylar, turn it on, and start scanning the storms as they're developing and or as they're producing severe weather.
I didn't realize how much went into tracking the storms, chasing the tornadoes. That was pretty impressive.
The radar itself is pretty complete. All we've had to do is make some customizations on the software side and on the physical deployment of the radar in order to meet, our research objectives. There's a lot of interest in the weather community for understanding phased array scans of weather because they can be done generally faster and more arbitrary.
Phased array has not been implemented as such in meteorology community and for collection of data from supercellular storms.
And the interest is being able to rapidly update this picture of the storm, say every 30 seconds. To do that with a conventional scanning radar is really impractical.
One thing that was really advantageous is that we were able to make Skylar portable, so actually taking it into the field in close range to severe thunderstorms rather than deploying it in a fixed spot and waiting for the storms to come to us. And then that enabled us to maximize our opportunities for data collection in the storms that we encountered.
Do you see the radar, Robin? We have visual on the wall cloud.
I could feel the changes in the temperature, changes in the wind patterns, everything, the cloud motions. So all of which is very much essential for the eventual formation of tornado.
Skylar has been one of the easiest radars for us to work with in terms of its deployability. We're able to deploy it very quickly, get it set up and scanning just in the matter of a few minutes.
Gives us better quality data so we can just understand what's going on in the storms better, which will ultimately let us see how these storms are changing and functioning. For example, this year we saw 2 storms kind of merge together, and we just have better resolution data.
I mean, we just get the raw data, and then we have to process it and form the weather products, and then we hand that over to meteorologists who then look at it and say, all right, here's what the weather was doing at the time.
The impact of having these rapid scans inside the supercell really cannot be overstated. Skylar is definitely meeting our need for getting rapid scan polarimetric updates in supercells in a way that no previous mobile radar I've worked with has. All right, so that's that. Just to give you a quick view of what kind of data we get with this radar. So this is just to orient you. We have a supercell coming at us. These are some data that my students collected, and they actually had to get out of the way of the storm. It turns out they're actually good at getting too close to it. So the amphitheater type shape to the scan here is actually the inner edge of that sector that they're able to scan, but you do see the ZDR column kind of poking up through the storm as it's coming toward them before they have to evacuate. So I had to tell them to kind of back off a little bit and try to top out the storm and get not quite so close. So just to wrap things up, storm chasing has very wide appeal. A lot of folks like to go out and storm chase and enjoy the spectacle. But if you are wanting to, contribute to the science, I would encourage you to get National Weather Service Storm Spotter training, and you can do that through weather.gov. I believe they only have a few more in-person training sessions left for this season, but you can also find a lot of the Storm Spotter training videos on YouTube. Most of the offices will have videos, and the ones out of the Weather Service office in Norman are particularly good. So I highly recommend those. Spotter training generally takes about 2 hours, and it's free, and you learn a lot about storm anatomy and how to observe storms safely without, wrecking your car or getting yourself hurt, and how to report useful information to the Weather Service that they can actually use to make actionable warnings information. So they can say things like spotter confirmed tornado, confirmed by a trained storm spotter, that kind of thing. So join and find mentors within your local storm spotting organizations. Spotter training is a good way to connect with those kind of people. If you want to report your observations to the Weather Service, there's an app called MPing, Meteorological Phenomena Identification Near the Ground. Was not originally developed for storm spotter applications, but they added it to that. There's also a Windows-based app called Spotter Network, which if you have a GPS, you can GPS locate your reports. And always remember, when you report stuff to the Weather Service, make it specific, accurate, timely. Tell them what you know and not what you don't know. And always remember safety first. This is something that my advisor really hammered into me when I was a graduate student. There is no photograph, there is no piece of data, there is no video that is worth risking your life and limb for. There will always be more storms, and you can always go chase another day. If you ever feel unsafe, always back off and give the storm a wide berth. You're speaking to somebody who was nearly killed by the El Reno tornado of 2013. It almost killed me, my husband, and my unborn child. We just barely escaped with the inflow jets of that tornado licking the back end of our car. That is an experience I'm not proud of, and I don't want to repeat it. So just to close out, I just wanted to say that storm chasing, for me, storm chasing, spotting, it's primarily about science. I love the science of learning how storms work, lifting the hood on them and finding out what makes them work. But I also just admire nature. I love being out in nature, being out with my friends in nature, and just being able to admire what the atmosphere can do. So with that, I will close out my talk and open it up for questions if we have time.
Robin, we have a great question here in chat from Kathleen, who has asked if you could please define derecho again.
Absolutely. So a derecho is a particularly long-lived squall line, which is very powerful because it's reinforced by a very strong rear inflow jet, and it can persist for many, many hours. Usually the rule of thumb is greater than 12 hours. And there's a great website associated with the Storm Prediction Center called About Derechos, and they have a great FAQ on kind of what constitutes the official definition of a derecho, but it's long linear storm which persists for 12 hours or more and produces strong gusty winds.
All right, thank you so much. And Sarah would like to know, with all of your technology, in your opinion, why do we still lack sufficient lead time for large tornadoes?
Okay. Well, I would actually challenge the premise that we don't get a lot of lead time for large tornadoes. I actually think that the largest ones, that your EF3s, 4s, and 5s generally are very well warned. Our probability of detection of those is close to 100%. and our lead time on those is in excess of 25 minutes. It's really the short, quick spin-ups that we're really having a tough time kind of nailing down. And those are the ones that drive our false alarm rates up so high. So these very quick spin-ups, maybe that are not well worn, not well seen. There's a few factors that can really play into that. Number one is, location. And the Southeast United States has a higher proportion of these unwarned tornadoes, or warnings with low or negative lead time. Meaning that the warning is issued after the tornado is already formed. We generally have pretty good lead time on the largest tornadoes. It's the small ones that we really have trouble getting a hold of, and that are driving our false alarm rates up. Another factor that contributes is also distance from the nearest radar. So we have a network of 122 NEXRADs, or what in my parlance we call the WSR 88Ds, because that's the model number of the radar. Those are located all across the United States, the lower continental 48 United States. There's a few in Alaska, a few in Hawaii, one in Guam, a couple in South Korea. But the ones stateside are the ones, they pretty much cover the entire lower 48 United States. And but there's still some gaps in between those. And those gaps are usually as a result of topography. So think like the Intermountain West, or places where, say, for example, here in Lafayette, Indiana, we've got our nearest radars are in Indianapolis and Chicago. So if you were to draw a line between those two, and draw the elevation of the lowest radar beams, that actually crosses about 1.5 kilometers above our heads. So we're actually missing the lowest part of the atmosphere where tornadoes tend to develop. And so that was why I put in a proposal and eventually got funding to put in a gap filling weather radar here at Purdue. We're still kind of working on getting those data in front of the Weather Service. There's a lot of bureaucratic red tape involved that I don't want to go into, but the idea is that we're filling that lower atmospheric observing gap between the Weather Service radars. So even though the horizontal extent of each radar's coverage area does cover Lafayette, we're still kind of missing a lot of stuff that's going on at the low levels. So that's another contributing factor, is just distance from the nearest radar, that contributes to some of the missed warnings and missed detections. But honestly, they're very few, and especially on really high-end chase days, you're going to have literally hundreds of chasers out there, people with cell phones and cell phone video that can send their reports to the Weather Service, can tweet the Weather Service pictures, and pictures are worth 1,000 words, videos are worth 1,000 pictures. So it's very rare that, during peak storm season, that any tornado is really going to get missed per se. But again, it's these really low end marginal setups where we're not expecting big outbreaks. Big outbreaks are generally very well forecast. It's the smaller ones that we really have trouble with.
All right, our next question is, I watched the storm radar and I noticed that storms seem to split to go around Indianapolis. Why is that? All of the concrete and buildings and heat from those?
Okay, so in general, storms do not feel the influence of cities very much. And if you think about it, a city covers a relatively small area. Yes, it is a heat source, but that's particularly at night when storms are less likely to form. What you're probably seeing is the effect of what are called ground clutter filtering systems that are installed on most of the weather radar softwares that we use. And those tend to kind of tamp down the reflectivities in and around large cities, because it mistakes high reflectivity signatures from real storms, hydrometeors, as being from buildings or from trees or things that are close to the radar that are not meteorological. Wind turbines, for example. Those things can actually trick radars. And so we actually have pretty good filtering systems to get those signals out of our weather radar data, but they're not always perfect. And sometimes they do scrub out severe weather signatures when they pass through large cities. I will also say that there is a phenomenon called sort of the meteorology school phenomenon, which is where everybody feels like storms split and go around their town. I've heard this from all the way from Maine to Oklahoma, and I've lived in a lot of different places. People always seem to think that the storms split and go around them. But you also have to think about all of the times that the storms didn't split and they did go over you, and they did produce copious rainfall and large hail and lightning. So it's a matter of kind of selectively remembering the times when maybe you were hoping a storm would hit and then it just happened to barely miss you, or it turned. And storms do change direction occasionally. That's another thing supercells are very notorious for doing, is just kind of hooking to the right. And that's because of the pressure gradients inside them. I won't get into the technical specifications of that, but so there's a lot of different things that can lead to a perception that storms are splitting and going around your town, but not all of them are based in reality, is all I'm saying.
If you have any last questions, we're wrapping up this evening. Please feel free to put those in chat. We'll wait just one more minute for any last minute questions. We would like to thank you all so much for joining us this evening for this special presentation by Dr. Robin Tanamachi. And all of this fascinating information will be recorded and posted on the library website soon. Make sure you check us out at carmelclaylibrary.org for information on future virtual and in-person events. We'll see you next time.
Be prepared, not scared.